Hello, and welcome to Astronomy 100. In this segment, we're going to continue our discussion about spectral lines. And if you recall from a previous segment, it was Bunsen and Kirchhoff, Robert Bunsen and Gustav Kirchhoff, who discovered that when you look at the lines that come from a chemical element, it's revealing the nature of that element. And so the pattern of lines helps us know what element it is. Each element in the universe has a unique pattern of lines. And so from this, they were able to identify that the sun is showing us all of the elements that it's made out of. And it's a combination of 74 different elements, and the patterns are all mixed together. Now, the one thing that they couldn't figure out is the physics of this. And the reason why is because physics, the knowledge of our universe back in 1859, had just not progressed far enough for us to fully understand the physics of this. But what Kirchhoff was able to do was to do some experiments that would show us why sometimes the lines appear dark with a colorful background, or sometimes appear colorful with a dark background, or sometimes you don't get any lines at all, you just get nothing but a colorful background. And so his experimentation led to 3 rules that today we call Kirchhoff's laws of spectral lines. So what I'm going to do is walk you through each of these and show you why they are what they are. So let's start with the first one. You'll notice that in this example here, we have a colorful spectrum. We have red, orange, yellow, green, blue, violet, all of the visible colors, but no lines whatsoever. This is what we call a continuous spectrum. And the words are obvious. It is a spectrum of color that is continuous. No dark lines, no breaks, but continuous. And Kirchhoff discovered that the way to produce this is that you must have either a hot solid material, a hot liquid material, or a hot opaque gas. If any one of these 3 conditions are true, the material will give off all of the colors with no breaks, otherwise known as a continuous spectrum. So what I'm going to do is show you 3 examples and give you an idea of what each of them is in reality. So here's an example of a hot solid. An incandescent light bulb is a source of light that has a very hot piece of metal. And when this metal gets very hot, it begins to glow, and the light that we see is coming from the fact that it's a hot metal. So this satisfies Kirchhoff's law for a continuous spectrum because it is a hot solid, a hot piece of metal that is giving off light. So a standard incandescent light bulb is a good source of all the colors, continuous, all of the colors of the spectrum. An example of a hot liquid would be volcanic lava. Now remember, this is normally a solid, but rock at a very high temperature becomes a liquid. And you'll notice that this volcanic lava, this liquid rock, is glowing with light. The light that you see coming from it is because this is a hot liquid. And if you had the ability to look at the light from this volcanic lava flow through a spectrometer, you would also see all of the colors of the rainbow with no colors missing. It would be a continuous spectrum. A third example is a hot opaque gas. Now, to fully understand this, we have to remind ourselves what the word opaque means. Opaque means that you can't see directly through something. So if a gas is opaque, that means light can still work its way through, filter its way through, but doesn't directly go through without anything blocking it. So to fully understand opaque might be helpful to think of the word transparent. Transparent is sort of the opposite of opaque. Something is transparent when nothing blocks any light that goes through it. And opaque would mean that light works its way through, but has to work its way. It can't directly go through. So deep down inside of the sun is a very good example of that. The gas down deep inside of the sun is very, very hot, and it is very dense, and so the gas is opaque. And so the light that comes from the center of the sun working its way through this hot opaque gas actually ends up giving off all of the colors of the visible spectrum. Every one of those colors is going to come out of the sun, But at some point, some of those colors get removed because we've already seen a moment ago that the sun's surface produces light where some of the colors are removed. And we'll talk more about that in just a minute. So a hot solid, a hot liquid, or a hot opaque gas, any one of these three will produce a continuous spectrum. Now, if we were to do a mock-up or do some sort of a laboratory experiment, we could do it with an incandescent light bulb. What you're looking at here is a regular incandescent light bulb. Pass the light through a slit, pass it through the prism, and you will get all of the colors with no colors missing. So this part right here is essentially what a spectrometer is doing. It's just displayed for you by the individual components in this illustration. Now, Kirchhoff also discovered that on some occasions you can get a colorful background with dark lines, meaning there are places where color is missing. And this is what the surface of the sun shows us, if you recall from the first picture we began with, is there's a very colorful background with various colors that are missing. This is called an absorption line spectrum, and it's really critical at this point that you understand the terminology correctly. The word spectrum means a range of something, and each of these dark lines are called absorption lines. So think of this as one phrase or one term. So that is an absorption line, that is an absorption line, these are absorption lines. Altogether, this is an absorption line spectrum. So an absorption line spectrum is produced when you have a cool transparent gas in front of a source of continuous light. So the idea is start with a source of all the colors and then put a cool gas that is transparent in front of it and let the light pass through that. The best way to sort of see what we're talking about here is to go back to the illustration again. You'll notice that we have the incandescent light bulb, which is the source of all of the colors. We pass all of the colors through a cloud of gas that is cool in temperature, and the light that goes through the cloud then goes through the slit, goes through the prism, and what you'll notice is that you get the colorful background, but various places where color is missing. So each of these dark lines are called an absorption line, or the whole thing is an absorption line spectrum. So cool transparent gas in front of a source of continuous light. The third example is the one that we saw in the last segment when we took some video of the emission tubes that give off light, and then we look at them through a spectrum, or excuse me, a spectrometer. And so what you'll notice is that we had a very dark background with very specific colors that were present. And so this is called an emission line spectrum. And the reason why is because these lines are called emission lines. So emit means to give off. And so this is a color that is given off. This is a color that is given off. This is another color. So individually, that is an emission line, that is an emission line, that is an emission line. So collectively, this is an emission line spectrum. Now, to produce an emission line spectrum, Kirchhoff discovered that you needed a hot, transparent gas that was sort of low in its density. But what's critical to know is that it is a hot, transparent gas where the gas cloud is the source of the light. So the gas itself is the source of the light. Then what you get is an emission line spectrum. So to show you the cartoon version of that, what you'll notice is the light bulb is now gone. The reason is because the cloud itself is the source of the light. So we have a hot cloud of gas, the gas is glowing, the light that the cloud gives off goes through the slit, through the prism, and then what we end up getting is a dark background with only certain colors present, and otherwise known as an emission line spectrum. So what we end up getting is one of three varieties. And so what Kirchhoff discovered is that in nature, we can only get one of these three choices. When you look at something, it either produces a continuous spectrum, an absorption line spectrum, or an emission line spectrum. There is no fourth variety. You can have hybrids of the two, but you can't really have a fourth variety. And so what Kirchhoff was able to figure out is that nature has a way to produce different ways of showing us lines. But once again, Kirchhoff really didn't know the physics of why this is happening. And what we're going to find out is that it really requires the physics of the 20th century to make all of this make sense. But let me show you one clue before we wrap this part up. Notice that the absorption line spectrum that we're showing you here is specifically the one for hydrogen. So this is a hydrogen absorption line spectrum. The one that we showed you that is an emission line spectrum is again specifically the element hydrogen. So this is the fingerprint or the pattern that hydrogen produces. But notice when we compare the middle one with the bottom one, the absorption line spectrum with the emission line spectrum, you'll notice that the colors that are missing are the colors that are present when it comes to the emission line spectrum. So something is happening in this situation that forces the colors to be removed, but something is happening in this situation that forces those same colors to be given off. So you'll notice that the pattern for hydrogen is the same. It's just whether or not it's a dark line pattern or a bright line pattern, but the pattern is still the same fingerprint. So when we look at the surface of the sun, we are looking at an absorption line spectrum, but the patterns of all the elements can still be identified, even though it's a dark line pattern as opposed to a bright line pattern. So Bunsen and Kirchhoff could only take us so far. They're only able to show us some laboratory experiments that reveal part of the mystery to explain the physics of why atoms are doing this and how they produce the light that they do is a bit of a big explanation. So what we're going to do is save that for next time. We're running a little short of time, so we'll pick that up next time. I hope you'll join me.